Thank you, the organizers, and good afternoon to everybody. So, particle in cell simulations of plasma instabilities, and why the peak or particle in cell. It's because there are, I mean, from astrophysical point of view, there are several astrophysical sites. For example, planetary magnetospheres, solar corona, astrophysical jets, supernova remnants. So in these sites, the density is very much smaller, and as a result, the mean free path is large there. So they happen to have collisionless. They happen to host collisionless plasmas, and what will happen in collisionless plasma or for a large mean free path is that, as a corollary, the particle distribution will not be will be non-equilibrium. What do I mean is the following. So if by any process, if the particles are getting energized, then they don't care about the background Maxwellian distribution, background particles which are having Maxwellian distribution. They will have their own deviation from the Maxwellian, which is called thermal distributions. And what could be the process of energization? Okay. It's not working. Okay. So yeah, what could be the particle energization processes? It could be magnetic reconnection. It could be magnetic reconnections where the particles are getting the magnetic energy. The particles are getting energy from the magnetic magnetic energy inside the systems, or it could be shocks where the particles are getting energy with the direction from the shocks, and the free energy in here is the flow energy in the shocks. So if we want to study this kind of phenomenon in collisionless plasma, then we need to explore the particle in cell technique, or there's a direction. Okay, so or if we want to tap if we want to tap the energy at very smaller length scale or time scale in plasma, then we must explore this peak simulation. One example could be counter streaming beams. By counter streaming beams, I mean, for example, two electron beams, their velocities are having same but in opposite directions. So in fluid picture, they are not moving at all because their average velocity is 0. But we will see next that they have a lot of free energy, which if we perturb the system, then the perturbation will grow. So to get this perturbation and growing perturbation in these counter streaming beams, we have to go to the smaller scale, and hence we have to explore the peak simulation. So how does it work? Okay, come on. Yeah. So how does it work? So now we have, instead of so in MHD or magnetohydrodynamical simulation, then we have only the grids. I mean, we discretize the equations and then we have grids and all. Now we have grids as well as the particles. So particles are embedded in the grid and they are moving in the there. So for example, here the blue and the red colors represents the opposite particles. So the grid and the particles, they will talk to each other. The flowchart is like this. We know let's start with from here. So the particles will evolve according to the Newton's equation, and so we know the velocity and or momentum and the position of the particles. And then once we know the position and the momentum of the particles, we interpolate those to the grid to get to know the charge and the current density in the grid. And once we know the charge and current density in the grid, then we get to know the fields from the Maxwell's equation. And then from the grid, so we want to check what happens to the particle in these updated fields. So we gather the forces, or we have to interpolate those fields from the grid to the particle to get to know what happens to the particle from the updated fields. and then again it goes on like that. So this is how the peak works. I mean, this is the basic I mean, the very basic feature of peaks. And so with this method, I will show you a couple of plasma instabilities. And I used WarpX, which is available in online. I mean, sorry, which is I mean, free. You don't have to do anything. So one is Wavell instability, where you have uniform plasma, and it contains two counter-propagating electron beams with an immobile ion in the background. So the beams along x direction, it the velocity, and along along negative x direction, they have the same velocity but in opposite direction. So what will happen if we perturb the system? For example, if we with electromagnetic wave and the perturbations are, or the transverse component of the perturbations are there, then what will happen is that the perturbations will grow and they will grow exponentially, and the maximum growth rate is this one. Here gamma is the Lorentz factor, and beta is velocity by light speed, and omega p is the plasma frequency. And if we do that, sorry. Oh. Yeah. If we do that, then from our from the WarpX code or from peak code, what we get is that in along y-axis it is the magnetic energy density, along x-axis it is the time in the unit of plasma frequency. So these three curves, the continuous curves are for numerical value or from the simulations for three different Lorentz factor. From here also we get to see, I mean, beta is root over of 1 minus 1 by gamma square. So it's basically kind of scales as root over of 1 by gamma to the lowest order or to the highest order. So meaning to say that as the gamma increases, this slope decreases and they get saturated, and some other instability is taking place. So now y-axis in the log scale, and so this one is the Wavell instability. Now, so one point is that here in the Wavell instability there was no background magnetic field. The perturbations are, if you give the perturbations, then the perturbations are growing from the free energy available due to the velocity and anisotropy in the system. But now we study the tearing instability. Here, okay. So here the equilibrium quantities. I mean, there is a background magnetic field. It is like this. Yeah. So this is the background magnetic. This upper portion of the figure is the background magnetic configurations. Where it has the density background density is like this, and lambda is the current set with. So the energy balance is the magnetic energy mostly outside the current set equals with the thermal energy, where theta is in dimensionless unit, and then the velocity which we'll get from the current background current is this one. So this is all the background quantities. Now, if we part up these configurations, this is in two-dimensional. So all our simulations are in two-dimensional. Then what will happen? This background magnetic field, they will they will get teared apart, and a small island will formed, and they will coalesce with each other and release huge amount of energy. That we will see in the movie, in this movie. So this is the isocontours, and this is the color plot. So we are seeing that at the very I mean around 0, there are a smaller formation of island is going on, and they are increasing in size. And after a few times, they will we'll see that they will merge, and at that point they will release huge energy, and the particle will get the energy from then. So yeah, now they are getting coalesced, and then they will release the energy, or whenever there is magnetic topology breaking, and then they are getting energy. And So yeah, so here what I'm showing is that x-axis is the time in units of plasma frequency, and y-axis is the energy. So this one is the field energy, electromagnetic field energy, and this one is the particles energy. So initially they were constant with respect to time, but as the field energy is decreasing, the particle energy is increasing, and it's going on up to this time. And the total energy is, of course, the sum of these is same. So these two instabilities, I mean, I have studied till now, and in future, so I started with the motivation that the particle distribution will not be Maxwellian. So I am yet to obtain these particle distributions in those cases, particularly in the tearing instability. And I did this all the Weibull instability and this tearing instability for beta, which is the thermal pressure by magnetic pressure less than 1. We want to do that for beta to be greater than 1, particularly for non-relativistic case. In the earlier cases that I showed is a relativistic one, and we want to apply this to the galaxy clusters, where the particle acceleration could be from the reconnection or tearing instability. So this is my future directions. Thank you.